Okay everyone, today I'm going to be testing if light can be black. So in order to understand this experiment today, you're going to have to let go of all of your preconceived notions about color. So the first thing you need to understand about color is that color is not a physical property. Color is only something that goes on up here. There may be certain wavelengths of light that correspond to a certain color that we recognize, but color in and of itself is not a physical property. And this is the reason why when I see this dress, I say for sure this is a gold and white dress. But then a bunch of other people say, no, this is for sure a blue and black dress. The reason for the wide discrepancy in the color of this dress is because we all perceive color a little bit differently, and it has to do with our preconceived notions. So because of this fact here, I want to show you a cool experiment to show you that light can actually be black. Okay, so I've got here on my phone a pretty bright light. You can see I can illuminate things with it. So nobody would disagree that this is a white light. Okay, so here's my phone again. Let me show you how I can turn this white light into black light now. 3, 2, 1. What color do you see now? So now the phone looks completely black. But when I turn the background light off again, it's white. So just by shifting the background light, you can turn white light actually into black light. So this isn't some kind of trick. I was keeping my screen at the same intensity whether I had the backlight on or not. And this would actually be the same result whether you're viewing it through the camera like you guys are doing, or whether you're just viewing it in real life like I'm doing. But because your eyes are a lot better than a camera at adjusting for backlight, you actually have to have the phone a lot dimmer for it to appear black. And what I just showed you may seem trivial, but it's actually a really important point. This means that black is actually a shade of white, or white is a shade of black. So black and white are actually just different shades of the same thing. And you already know this if you've ever watched a movie on the big screen. Have you ever thought, how do they project black onto the screen? So let me use my little mini projector here to show you what I mean. So for example, in these parts that you see in this video that are black, are they really black or are they just less white? Well, let's test it and see. Okay, so on the screen I have what looks like a white background with a black dot in the middle. So is this black dot actually being projected on here? Well, look at this. So if I raise the exposure here, you can clearly see that this black is actually a light. See, when I block it with my hand, there's clearly a shadow in the center here. So this black is not so black, it just looks black compared to this brighter light back here. The same thing that we saw with my phone and the bright background. One more way to confirm this is to get my head right in the middle of the black and look into the light, and it's actually bright, I can see it. So here's what it looks like in the white, and then when I move into the black circle, here's what it looks like. So you can see that black is just less light. Here's the white, and here's the black. White, black, white, black. So you can clearly see that the difference between white and black is just how much light is there. So there's my proof for how white and black are different shades of the same color. But the problem is that white and black are not really colors, because white is just a combination of all the colors of light. Or said more correctly, white is just what our brain perceives when we see all of the colors of light at once. So this is why when you shine red light, green light, and blue light together, it makes white light. And now this is where it all comes together. I always knew that when you combine the primary colors of light, like red, green, and blue light together, you get white light. But in school, I'd always get confused in art class, because when you mix red paint, green paint, and blue paint, you don't get white paint, you get black paint. And how you'll usually have that explained to you is because when you mix paints, it's called subtractive color mixing. And when you mix light, it's called additive color mixing. And so you get different results. But actually, it's not so different, because no matter what, whether you're seeing paint or a light, all of it is light actually hitting your eyes. So it shouldn't really matter whether it's paint or light, right? Well, the truth is it doesn't matter. So when you mix red paint, blue paint, and green paint together, you get black paint. But as I just showed you, black is actually just a shade of white. So what that means is that the color pigments that you put into your paint are absorbing most of the light from around the room. So compared to the bright room around it, that paint looks black. When in reality, there's a small amount of light bouncing off of it back to your eyes that is actually white light. But it's really confusing to think of it that way. So that's why artists don't think of it that way, and they just have their color palette and they mix it according to subtractive color mixing. So basically what this means is when you have some red, green, and blue pigments that are brighter than the ambient light in the room, it's going to look white to you. But if you have those red, green, and blue pigments that are absorbing more light than is in the ambient room around you, it's going to look dark or black or even gray. And since for paints, since they absorb the light from the room, they're always going to look darker from the room. And so that's why paints always use subtractive mixing. But for something like mixing light together, it's always additive mixing because it's always going to look brighter than the room around it. And so once you realize all of this, it all kind of comes together and makes sense. For example, is there such a thing as brown light? Well, it turns out that brown is actually just a shade of orange. It's just darker. So in order to have brown light, you just need a dim orange light. And this brings me to my final point. If color is all in our head, how can we be sure that we're all seeing the same colors? This is an interesting thought. In fact, Vsauce a while ago did a whole video dedicated to just this one concept. So we can never truly know that the color that we are seeing is actually the color that someone else is seeing. We can confirm that they're the same wavelengths because we can measure wavelength, but we can never know the color that someone is actually seeing because color is just in our heads. And that means that light can be black because black and white are also in our head. Hey everyone, thanks for watching another episode of The Action Lab. I hope you enjoyed it. If you did and you're not subscribed yet, remember to hit that subscribe button. And if you'd like to be notified when my latest video comes out, remember to hit the bell button. And remember to leave me any comments or questions or suggestions you have for future videos in the comments section, and I'll see you next time.